Yes, hope all of us are doing great. My name is Ernest, and I'd like to welcome each and every one of us to my channel of Ernest Sciences and Mathematics TV channel. In our discussion today, we're going to look at one-dimensional simple harmonic oscillator. And this specific concept is going to be very relevant in most of our discussions, especially whereby we're going to look at a concept that will assist us understanding the interaction of elementary particles. Now, in our previous discussion, we have mentioned the concept of atoms and molecules. Now, the motion, of course, of this specific or the one-dimensional simple harmonic motion or a simple harmonic oscillator is going to be assisting us in trying to interpret, of course, the motion of such a kind of particles which have basically categorized as elementary particles. Now, apart from that, we're going to see that in order for us to understand the sounds of various instruments, especially musical instruments, we're going to require the concept of this specific concept of harmonic oscillator in order to understand that specific concept. Now, among others, we're going to see also that for us to interpret the concept of radio and TV communications and the nature of light and colors, among other areas like study of vibrations in car engines, shock absorbers, and the brain waves, that is going to play a vital role in order for us to understand it. So therefore, that creates a relevancy for us in trying to discuss this specific topic. And of course, we're going to consider this particular illustration which I've given, of course. It's going to be, of course, an example from the previous discussion we have had on the concept of potential energy, kinetic energy, and work. And that is going to create for us a precedence in trying to discuss this specific topic. Now, we're going to consider a classical particle of mass m, which I've illustrated on my right side of the board, which is going to be attached to a spring, whereby we're going to consider that this specific spring is going to be a lightweight spring that is going to obey Hooke's law. Now, in this case, we have mentioned this specific term in our previous discussion, and this was basically the relationship between the force applied and the distance which is going to be, of course, achieved due to this specific, of course, effect of a force. And we had said that basically this can be given in terms of the product of a spring constant given in terms of k. And then we're going to have the distance moved, or the difference in distance given in terms of x given as such. Now, in this case, this is going to be a formula that's basically going to represent the concept of Hooke's law, which deals with the concept of force and, of course, the distance. So basically, this can be given as a proportionality given in terms of force and distance. And that, of course, is going to create for us a precedence of discussing this concept of one-dimensional simple harmonic oscillator. Now, considering that one, we're going to ignore the mass of the spring in that case. And of course, as I mentioned, of course, we're going to be assuming that relative to the particle, the spring is going to bear minimal mass, or in this case, no mass. And of course, we're going to see that we can find the frequency and amplitude of this specific kind of motion. So in this case, if we see that if this particular force is stretched and released, it's going to go back to its initial position and keep on going in that vertical and, of course, vertical position in a repetitive way. So we can find the frequency and amplitude of a motion. Now, we had discussed these specific terms in our discussion on the concept of a wave or anatomy of a wave, whereby I had mentioned that these are the number of cycles per second, and the concept of amplitude is the displacement from the equilibrium position of a wave. So we had considered this specific kind of a wave, whereby we have said that the displacement from the equilibrium position, assuming that this is going to form our equilibrium position, and y is going to form our displacement from this specific point, and therefore the amplitude is going to be the maximum displacement from the equilibrium position given either in the positive or negative direction. So for us, from this specific example, then therefore we can find the concept of a frequency and amplitude and try to see how we can be able to describe this specific harmonic oscillator in terms of those specific motion. So in terms of energy, therefore, we can illustrate this specific spring, whereby we are going to find the total energy of vibration of this specific spring, whereby this specific mode is going to be, of course, oscillating between the maximum and the minimum position due to the stretching of that spring from the initial energy which we had mentioned. So in this case, this is going to be given in terms of the total energy. And this, from our last discussion, I talked about the concept of a mechanical energy which basically is the sum of a potential energy and the kinetic energy. So in this case, this is going to refer to our kinetic energy, and then this is going to be referring to as our potential. So in this case, we had mentioned the concept of elastic potential, and then of course we are going to consider this, of course, kinetic energy. But in this case, this is going to represent what we refer to as our Hamiltonian, which is basically the total, the summation of this potential energy for kinetic and potential energy given as such. So from our previous discussion, we had mentioned that we can represent kinetic energy as a half the product of mass and the square of velocity given as such. Whereas we said that for the elastic potential from our previous discussion given in terms of V is equivalent to the product of a half kx squared, where k is a spring constant and x is the difference in distance from x initial to the x final. Therefore, this specific Hamiltonian can be represented in terms of these two specific notations, whereby we're going to have kinetic energy given in terms of a half mv squared plus the potential energy given as a half kx squared given as such. But from motion equations of motion, we said that x representing, if x represents the distance or displacement, we're going to consider the first derivative of dx over dt with respect to time. So the derivative of x with respect to time is going to give us a velocity, and therefore we're going to consider this specific aspect of dx over dt in terms of velocity, and therefore our Hamiltonian will be equivalent to 1 over 2 m dx over dt, and this is going to be the square of this one representing the square of velocity in this particular case. So we're going to add this one to kx squared given as such, and that is we represent our specific representation for the Hamiltonian. So therefore, for the system, since we are going to consider this system as a closed one, we're going to see that there's not going to be an exchange of energy between this specific, of course, setup and the outside environment, and therefore we can consider the derivative of this particular Hamiltonian, which we have given in terms of h with respect to time, given as, so dt, the h over dt is going to be equivalent to 0 due to the closed system nature of this specific setup that we have mentioned. Therefore, in this particular case, we can consider the derivative of this specific section for the right side of our equation and try to see what we are going to achieve from this specific equation. So this is going to be appearing in terms of, perhaps because of our space, I can limit this one. So we're going to have this one basically, which is going to be dh over dt of this specific, of course, section which we're going to give in terms of the derivative of this is going to be so I'm going to do a simplification of this. I presume that we understand some of the rules of derivatives from our previous discussions on the concept of course, differential calculus. So we're going to have that one given in terms of that one. So if we do a derivative of this x with respect to time, it's going to be a second derivative, and therefore that's going to be d squared x over dt given as such. And then we shall have this specific section for k. Perhaps I'm going to do away with this particular section. So we shall have this second section of this given as kx dx over dt is equivalent to 0. So this is going to be a representation of the derivative of this Hamiltonian, which we have given in terms of dh over dt equivalent to 0. As we said, there's no exchange of this specific energy with the outside environment. Now this is going to give us our final equation for the motion of a simple harmonic motion. If we consider this specific representation, so over kx plus this m d squared x. So this is going to be the second derivative with respect to time given as such, equivalent to 0. So this is going to form our equation for representation of the one-dimensional simple harmonic oscillator in terms of these elements of the second derivative, and of course the product over kx given as such. So in our subsequent video, we're going to consider some of the examples which we are going to come across, and perhaps we're going to use an evaluation set which is going to assist us in trying to understand the final implication of this specific equation. So kindly check our description boxes for various links of other similar videos. Subscribe and also engage us in the comment section, and also ring that notification bell for various updates on the concept of a one-dimensional symbol, harmonic oscillator, and other related content. So that is it for now, guys. Bye, God bless you. Catch us in our next video.